Hi, good afternoon, everyone. So today we're going to talk about the introduction to function. This is covering section 1.3. Last class we talked about, we completed section 1.1 and 1.2, where we talked about different Cartesian ordered pair, and we looked at some set Bilter notation, and we also talked about symmetry at a very high level. We looked at briefly what the relation is. So we are now getting into the introduction to function. As I mentioned, one of the core concepts in college algebra is the function. There are many ways to describe a function. So we're going to first look at the definition of a function. So the function definition, a relation in which each coordinate is matched with only one y coordinate. That is said to describe as y as a function of x. So that means there is only one arrow going from each of the point in the x-axis to a point in the y-axis. So let's look at this example here. So I have presented two relation here. This is in relation to the x-axis and y-axis. So looking at this relation here, in the first one, you see that negative 2 comma 1, 1 comma 3, 1 comma 4, 3 comma negative 1. Is this relation comply with the definition of this function? Or is this relation describe y as a function of x? The first relation, the answer is no, because if you look at, and here I kind of presented it in a table where we have the first column for the x-axis and the second column for the y-axis. If you look at each point in the x-axis, like negative 2 is mapping to 1, 1 is mapping to 3. Again, there is another one mapping to 4, and 3 is mapping to negative 1. You see that the same 1 is mapping to two different points in y, and it does not meet the definition criteria, which is each x coordinate matched with only one y coordinate. Therefore, this is not this relation does not describe y as a function of x. Now let's look at the second example. In the second example, we have negative 2 comma 1, 1 comma 3, 2 comma negative 3, 3 comma negative 1. So this one, it does present this relationship describe y as a function of x, because if you look at each of the x coordinate, each of these values are unique, and there is only one arrow coming from each x to the y. So therefore, we can conclude that this relation describe y as a function of x. So we use a simple technique called vertical line test. And what does the vertical line test do is it helps us to just quickly do a quick test, and it helps us to determine if this is if a relation represent y as a function of x. So the vertical line test said that if a set of points in the plane represents y as a function of x if and only if no 2 points lie on the same plane. So what does that mean? That if you have a graph, for example, here you can graph y is equal to x squared. So go ahead and in your graphing calculator, graph y is equal to x squared and see what do we get. It's going to be an open upward parabola. So now draw a vertical line. Now what is the vertical line? This is going to be in parallel to the y-axis, right? It's the straight line. So if you draw that vertical line and see how many places this line is crossing on the graph. If it's crossing the graph more than one places, then this relation, the function does not represent y as a function of x. If it's only intersecting the graph, if this line only intersecting the graph in one place, then we can conclude that this relation represents y as a function of x. So, and try another graph. See if you can come up with another function. How about y is equal to x to the power cube? Or maybe see if you can come up with another function that you can graph and see if, and do the vertical line test and see if it's representing once or twice. If it's intersecting in one place or two places, and what can we conclude from that? All right, the next, domain and range. So suppose that f is a relation which describes y as a function of x. And the set of x coordinates of the points in that function is called the domain of the function. And the points that are representing the y coordinates, it's called the range of the function. So here I have presented a function which is -3, 2, 0, 1, 4, 2, and 5, 1. So what are the, can you list out all the domains that we have in this function and list out all the ranges that we have? So if we look at the domain here, the domain are the x-axis, which is -3, 0, 4, and 5. And the ranges are 2, 1. Now there is 2 repeated twice, so we don't have to repeat it twice. And well, actually there is another 2 in the fourth order pair, so we only have to list 2 ones. So again, the domain is the set of x coordinates of the points, and range is the y coordinates of the points. Again, the domain is the list of the points for the x-axis, which is -3, 0, 4, and 5, and range is the y-axis, which is 1 and 2 in this case. So what is the difference between function and relation? So function is a special kind of relationship, and there is a very subtle differences between the function and relation. So all functions are relation, but not all relations are function. And the equation which describe the relation may or may not describe y as a function of x. We have seen in the previous slide an example where y did not describe, the function did not describe y as a function of x. So again, all functions are relation, but not all relation are function. The algebraic representation of function is possibly the most effective way to view them. So we need to process for determining whether or not an equation of a relation represents a function.
So in this example, there are a couple of examples that we're going to look at. So the first one is determine which equations represent y as a function of x. So the first equation we have, which is x cubed plus y squared equals 1. To solve this equation, we're going to get y by itself, subtract x cubed on both sides of the equation. That would give us y squared is equal to 1 minus x cubed. So now take the square root to both sides, and that eliminates the square root from y, and that leaves us with just y is equal to plus minus square root of 1 minus x cubed. So if you pick a value for x and plug it into that equation, because this is a plus and minus of square root of 1 minus x cubed, we're going to have two values of y. Suppose that x equal to 0, then y would be equal to plus or minus 1. So for each values of x, we're getting two values of y. So that means two arrows going from the same x to the y, which tells us that this equation does not represent y as a function of x. Now let's look at the second example. We have x squared times y is equal to 1 minus 3y. So we want to get the y by itself. So add 3y to both sides. that would give us x squared times y plus 3y equal to 1. So now factor out y. If we factor out y, we get x squared plus 3 is equal to 1, and divide both sides by x squared plus 3. Then we would have y is equal to 1 over x squared plus 3. Now in this case, any values that you pick for x, we're going to get only one values of y. Just go ahead and pick some test points for x and substitute into that equation and see how many y's values that you get. It's going to be 1 because y is, we don't have the plus minus issue that we had in the previous problem. This is just one values of y. So in this case, this equation does represent y as a function of x. All right, so that is all I have from this section. I would like you to go over the example problems we looked at, see if you can work out this problem yourself again, and go over the concept, and then work through some of the practice problems that I have assigned from end of this section. As you're going over the lectures and the notes and practice problem, if you experience any difficulties, make a note of that, and I would be happy to go over those sections and the topics again when we meet in class next time.
All right, section 1.4 talks about the function notation. So we learned that function is a special kind of relation, and each x coordinate is matched with only one y coordinate. And in this section, we're going to focus on the process by which that x is matched with the y, and we would look at different notation that are used in relation to the function. So when we talk about the function, there are three main parts of that function. A function consists of three parts. The first one is called the input. So input is it represented by independent variables, and sometimes we call it variable x. So all possible valid input values are in a set called the domain of the function. So again, input, like just think about, the computer language, the way the computer language works. We sent our, we're sending some command to the computer. Computer is taking it as input, and then it does the processing, and then it sends the output back. So input is something that you're, sending, providing some initial information to use that and go through that process and send an output. And that input, in the previous section, we looked at the domain and range. So input is called the domain of the function. And the output, it represented by assigning the results of the function to the dependent variable. Often that variable is y. So once we input the value into the function and we do the math, and we get a value which is considered the corresponding output for that given input, and the values that are in a set called the range. So these are the y-axis that we derive, and it's called the range of the function. And then the third part of the function is a function f is a process. And what does that mean? A process that maps each input value to one unique output value. And the process is often represented by it can be represented by a description. It can be an algebraic expression. Sometimes we can use a table to represent that, or even a graph or a chart. So y is equal to f of x is the output, which resolves by applying the process f as the input. So y and f of x, it's interchangeable. So the f of x, that is the function notation. So anytime you have used f of x equal to, let's say 2x plus 5, So when it's written as y is equal to 2x plus 5, this represents an equation, algebraic equation. And when you replace the y with f of x, then it becomes a function just by using that function notation. So that means you can use an input and process that function and find a corresponding output for that given input. Couple of more terms that we're going to talk about, which is the independent and dependent variable. So in this equation, y is equal to f of x. So the value of y is completely depending on the choices of x. And this x is often called the independent variable of that argument because you can pick any arbitrary values for x and use that as an input to find the corresponding output for that function expression. And because these x values are arbitrary number and it's called the independent variable, and y is often called the dependent variable because to find the value of y or the corresponding output, you need to rely on the input, because without having that input, we are not able to find the output. That's why y is called the dependent variable, because it is depending on um, the input from x. And when we graph the function, the independent variable, which is variable x, goes on the horizontal axis. So we know that the horizontal axis represents the x-axis, and y, or the dependent variable, it goes on the vertical axis, which is the y-axis. So let's look at this example here in the equation d is equal to g of t. So what do you think is the independent variable here? The independent variable is t, right? And what is the dependent variable? The dependent variable in this case is d, because we don't know what the value of d until we plug in t as an input to get the corresponding output that represents the d.
So we're going to look at a few examples here. Suppose I'm giving you a function of x equal to negative x squared plus 3x plus 4. I would like you to find and simplify f of -1, f of 0, f of positive 2. So what does f of -1 means? So -1 is the input to this function, and I wanted to input that -1 and find the corresponding output. So we plug it in -1 wherever we have x in the function. So that's -1 squared plus 3 times -1 plus 4, and that gives us 0. So the corresponding output is 0 when the input is -1. So now I would like you to stop the video and work on find the corresponding output when the input is 0 for f of 0, and find the corresponding output for the input 2, which is f of 2. So now let's look at example number 2. This time I'm giving you the input 2x. So again, replace the x in the function with the 2x, and then do the math. We get -4x squared plus 6x plus 4. Example number 3, this time I have 2 times f of x. So what is it telling us is that we have to multiply the function, multiply the 2 to the function. So we're going to be distributing 2 into the function, and that would give us -2x squared plus 6x plus 8.
Okay, so the third example here, we have f of x plus 2. So this time we're going to be using x plus 2 as the new input to that function. Okay, so wherever we have x in that equation or in that function, we're going to replace the x with x plus 2. So that's negative x plus 2 squared plus 3 times x plus 2 plus 4. So x plus 2, we need to FOIL this, and I'm sure everybody is aware of the FOIL technique. So x squared plus, once you FOIL it and combine the like terms, you're going to get x squared plus 4x plus 4, and bring the rest of the equation down. Now the next line, we have distributed the -1, so that's why, and eliminated the parentheses. So that's negative x squared, negative times a positive makes it negative 4x. Negative times a positive 4 makes it a negative 4. Plus 3x, now distributing the 3, so that's 3x plus 6 plus 4. And if we combine the like terms, we get negative x squared, negative 6 plus 6. Negative x squared, negative x plus 6. Okay, so now I would like you to stop the video and take about 5 minutes to work on the problem number 4, which is f of x plus 2. So this time, if you look at it carefully, I'm asking you to add 2 to f of x. And the second part is f of x plus f of 2. So in this example, you have to find the corresponding output when the input is f of 2. So that means you're going to plug in 2 into that equation and find the corresponding output, and that corresponding output would be added to the function notation. So work out that problem and let's see what answers you get. All right, the next thing we're going to talk about is the implied domain. So when we talk about domain, what do we mean by that? So domain is, again, remember when we were looking at domain just a few minutes ago, domain is the set of points which are on the x-axis, and the range is the set of points on the y-axis. So when we talk about the domain, by default, domain is all possible real numbers. It can be included, any possible real number can be included into the domain. However, we may have some circumstances, for example, let's say that you have a fraction, and as we know, this is the basic rule is that when there is a fraction, the denominator can never be 0, because if the denominator is 0, then you're going to have an undefined function, or it's not defined. So anytime we have a fraction or a square root, because if we have square root, we know that we can't have a negative number under the square root because that does not exist in the real number system. So we have to look at each of that equation and see, is there any condition that is not acceptable in relation to this function and equation. So in terms of if there is a fraction, then we know that the domain is all real numbers. So what we're trying to determine if there is any number which would make, if I substitute into my function, I'm going to get a 0 in the denominator. And as I have mentioned, 0 is not acceptable in the denominator in the field of mathematics. Okay, so again, the domain is all real number except any numbers that would make your denominator undefined, or if you're dealing with the square root, you can't have a negative number under the square root. Okay, so, and this set of numbers is often called the implied domain because, again, the domain is all real number except if there is any number that we can think of that's going to make my function undefined, then those numbers are excluded from the domain. So how do we find domain? Here is an example. So find the domain of the following function. We have f of x equal to x plus 4 and in the denominator, x squared minus 2x minus 3. So in the solution here, the domain, we know that this is a fraction, right? It's a rational expression. We have a numerator and a denominator, and we know that the denominator cannot be 0. So can you find any values where x squared minus 2x minus 3 is equal to 0? So basically we take to find what number is excluded from the domain, we take the denominator and we kind of set it to 0 and see if you're able to factor it. Okay, if you're able to factor it, go ahead and factor it. And if you're not able to factor it, then it is what it is. So once we factor the denominator, what do we see? We get x minus 3 times x plus 1. And I'm sure everybody knows how to factor a trinomial. And if you have any questions, see me after the class and I would be happy to go over that with you. So the factor of x squared minus 2x minus 3 is x minus 3 and x plus 1. So in that expression, if I substitute 3 into the first parenthesis, so 3 minus 3 times x, which is 3 plus 1. So we're going to get what? 3 minus 3 is equal to 0 times anything is 0, right? So 3 cannot be part of the domain because if we plug in 3, it's going to make my denominator undefined. What about x plus 1? What number would make that equal to 0? So if I bring in a negative x plus 1, or you can just think of it like I'm adding adding 1 to this. So that means adding a negative 1 actually. So negative 1 plus 1, which cancel each other out, and it's 0. So we also notice that negative 1 cannot be part of domain either. So to conclude this example, the domain is the set of all real numbers except the numbers that's going to make the denominator 0. So here the domain, and if you look at the bottom of this slide, this is one of couple of ways that we write the domain. This is called the set builder notation, the set of all x such that x is not equal to 3 and x is not equal to negative 1. So that means if I plug in 3 into that equation, I'm going to get a 0 in the denominator, which is not acceptable.
Sometimes, so here we're going to talk about modeling with functions. Sometimes we use the real life, we use the function to model real life scenarios. So here we're going to look at an example. In this example, it shows how a function can be used in the real life scenarios. And sometimes, especially in the manufacturing industry, you can actually make prediction in terms of what quantity that you need to produce to be able to earn certain revenues. So this kind of modeling is a useful tool to get insightful information and help making business decisions. So in this example, the height 8 in feet of a model rocket above ground, t seconds after liftoff, is given by h of t is equal to, it has two pieces of the function for h. The first piece is negative 5t squared plus 100t, if t is between 0 and 20. And it's 0, the second piece of the function is 0 if t is greater than 20. And this kind of function is called the piecewise function because you have one function but different pieces based on two different ranges of two different domain systems. So we're going to find and interpret h of 10 and h of 60. So what does that mean is, if the input is 10, again, what is 10 here? 10 is the time, which is in second. So what would be the height of the model rocket 10 seconds after it lifts off the ground? So the solution here is to find an interpret h of 10. So let's look at 10. 10 is your domain. So which one of the piece of the function do we have to use? And that is based on where the domain falls. So for the first piece of the function, the domain is between t to 20. So 10 definitely falls in that um, category. So we're going to use the first piece of the function, which is negative 5t squared plus 100t. So substitute 10 for t, so negative 5t to the power squared plus 100 times t. So doing the math, 10 squared is 100 plus times negative 5 is negative 500 plus 100 times 10 equal to 1000. And if you combine them two, you get 500. So what does that mean? The rocket is going to be 500 feet above the ground in 10 seconds after it lifts off.
Section 1.4. Now I want you to take about 10 minutes to work out some practice problem that are listed on the syllabus from 1.4. All right, the next thing we're going to talk about, section 1.5, which is the function arithmetic. Function has its own arithmetic, and the that we're going to look at, that following definition allows us to add, subtract, multiply, and divide. Okay, so like any other simple arithmetic, function has its own arithmetic, and we are able to add, subtract, multiply, and divide in the function concept. So the first bullet here, which is sum of f and g, and it is written as f plus g is the function defined by the formula, which is f plus g of x. So that means it's f of x plus g of x. So here again, in order to be able to add, subtract, divide, we must have two functions, right? So that's why we have a function f and a function g. So we are adding the two functions together. So that's f plus g of x. And then it's kind of distributing like f of x plus g of x. And then in a few minutes, we're going to look at an example to see how to solve problems using those arithmetic formulas. And then the second bullet, this is the difference of f and g. And it's denoted by f minus g. And that is a function defined by the formula, which is f minus g of x equal to f of x minus g of x. So this one and the sum pretty much work exactly the same way. The only difference is the sign. So one is all positive and one is all negative. The next two are product and quotient. So the product of f and g, and I'm sure you have product of f times g, denoted by f times g, is the function defined by the formula, which is f times g of x, which is f of x times g of x. So that means we are combining or multiplying the two functions together. And the quotient, this is the division of f and g, which is denoted by f divided by g, is the function defined by the formula f divided by g of x. And that means it's f of x divided by g of x, and provided that g of x cannot be equal to 0, because if the denominator is 0, then everything, then it's undefined. We can't solve it.
So in this example, we have f of x equal to x squared minus x and g of x equal to x plus 2. So we would like to find the sum of the two function with the given input 3. So f plus g of 3 is equal to, using the summation function, the formula, we're going to say f of 3 plus g of 3. So now what is the corresponding output for the f function when the input is 3? So in the f function, you're going to replace the x with the 3. So that's 3 square minus 3 plus in the g function, which is x plus 2, we're going to replace the x with 3. So that's how we get x, 3 plus 2. So now in the next line, 3 squared gives us 9, and then bring down the negative 3. And then we added the two number, 3 plus 2 is 5. And then further manipulation would give us 9 minus 3 is 6 plus 5 equal to 11. Now the second example, f minus g of x. So this time we're subtracting, so that would be based on the formula, f of x minus g of x. So in the f function, we're going to replace f of x, we're just going to bring down the f of x and replace the f of x with x squared minus x. And then negative sign, and then bring down the g of x. And make sure you put the parenthesis around it because you have a negative sign in front of it. So that means you need to distribute the negative 1. So now in the second line, distributing negative 1 and eliminate the parentheses, that would give us x squared minus x minus times the plus is negative 2. Now we're going to combine the like terms, so that's x squared minus 2x minus 2.
All right, so now I would like you to do these two problems here, division and multiplication. So for the division, again, this would be f of negative 4. Negative 4 is the input, and g of negative 4. And you have to find what's f of negative 4 means. So we take the f function and replace the x with the negative 4, and then do the math, and then use the g function and replace the x with the negative x and get the value. And the second example, which is f times g of 3. So this is equal to f of 3 times g of 3. And then determine what's f of 3 is, meaning that if the corresponding input is 3 for that function, then what's the corresponding output? That's what you need to find. And then do the same with g of 3. Plug in 3 for x into the g function and find the corresponding. Okay, the next thing is the difference quotient. So given a function f, difference quotient of this f is the expression. So that is, we have x plus h minus f of x divided by h. So we need to find the difference of quotient of f for that function that's given, which is f of x equal to 4x plus 3. So what does that mean is that we're going to be, that's the f of x function. So we're going to be taking f of x plus h minus f of x over h. We're going to use that x plus h as an input into that function that's given, which is 4x plus 3. So if you look at the last line where I have f of x plus h, so in that function that's given 4x plus 3, I'm replacing the x with x plus h, and then bring down the x, and then minus f of x into that quotient, difference of quotient expression, and problem a little bit more. So 4 times x plus h plus 3 minus 4x plus 3. So now we're going to distribute the 4 into x plus h. That gives us 4x plus 4h. Bring down the 3 and then distribute the negative 4, a negative sign, which is negative 4 times negative 4 minus 3. So if we combine the like terms, 4x and 4x cancel out, 3 and a negative 3 cancel out, all we have left is 4 times h. And in the denominator, we have h, so we can cancel out the h, and that leaves us with. So here is another example, another practice problem. So I want you to turn off the video and see if you can work out this problem. This time, the function is different, which is x squared minus x which is x squared minus x minus 2. So we're going to use x plus h as the new input for that function. And then we're going to minus that f of x into that expression. So let's see if we can